Hello everyone, can you hear me? Okay, great. My name is Aleksandr, and I'm going to talk today about semi-supervised learning, more precisely about object detection using semi-supervised learning. Possibly now it's not the most popular topic due to like self-supervised learning, Gen AI, etc. But personally for me, it's quite interesting, and I tried to use it before in my applications and challenges that I had before. So, first I will just remind what is object detection shortly. Later I'll go through ideas of what is semi-supervised learning, and later we'll go through some main approaches used there. And finally, I will talk a bit about current state of the art results. That's my plan for today. Okay. First of all, like I assume all of you know what is classification, what is object detection, but the idea is pretty straightforward. So classification, we have some image, we want to detect what is there. Capybara that you can see here, or I don't know, cat, dog, human, whatever. It's like first example. Second example, object detection. We not just want to say what is on this image, but we want to localize, want to say where is it exactly. I just put some bounding boxes, and below I just say some class. In this specific example, capybara, 3 of them in Barigui Park in Curitiba in Brazil, or human. So yeah, bounding boxes, like everyone, I assume, might know that it's just some 4 numbers. It can be like center, x and y, height and width. Okay. Now let's talk a bit about like what is semi-supervised learning, why, like what is the main idea. When we approach some supervised learning, we have some labeled data and we have some problem. So we apply algorithm, we learn from labeled data, get some classifier, produce result. But quite often we don't have too much labeled data, or it's pretty expensive. Like for those who worked in large corporation, you might know how complicated to get the budget, even if it's, I don't know, like 50,000 pounds, 1 million, whatever. For those who work in startups, I assume there is a challenge from other side. Might not be some money to invest in this. And I put some examples where this challenge exists. And like what causes this problem? First of all, like sometimes you need expertise. It's like quite hard to label images from medical research. I have no idea like if I have problems or not, even looking on the image. Another thing is time consuming. Again, not only time consuming, but you need to wait some time. Like let's say we are talking about advertisement. Like someone put ads, and can I be sure that this ads is good or not? Like after 1 hour, after like 10 hours, I might not be sure. Like maybe effect will reach like after 1 day or after 2 days, whatever. No, and resources I mentioned before, like sometimes it's about money. Like for instance, ads is opposite case. If you have some signal, you can just collect it and just later say like, was it good or was it bad? And like 4 examples, medical research I mentioned, industry inspections is where I worked before, when you have some refinery station or another production, and like, let's say you want to know if this specific structure has corrosion or not. As usual, most of the time, it's done manually. Like we hire some company, these people come, stroll around, look, take photos, and after that provide results. How we can automate it? Pretty straightforward. Send drone, take photos, collect detections, label them, connect this with location information again from drones. But again, labeling this data is pretty time-consuming, budget-consuming, etc. Advertisement I mentioned, and malware is another use case where you need expertise, so not everyone can reverse code and understand, is it malicious file or not? And again, it's pretty expensive. Okay, intuition behind semi-supervised learning, like we know there is supervised learning, we have labels, we have goal, we apply some algorithm, backpropagation, whatever, we are happy. Unsupervised learning, clustering, etc. I put here like third idea is like reinforcement learning, but just in gray because it's not related. But what if we apply some ideas from like supervised learning and unsupervised, or like kind of data, supervised and unsupervised, like when we don't have data, I don't know. So we'll get some semi-supervised learning algorithm. And how, like how we can approach this? First idea, like main idea of this, again, we have some like supervised loss functions and like unsupervised loss function. What if we combine them? For labeled data, we can apply like simple classification loss functions. For unlabeled data, some similarities. No, and when we are talking about data augmentation, again, my favorite example with capybaras, like if we have this image and do something with this image, in most of the cases, it will be the same. Like class, when we are talking about classification, still be the same. Like if I like crop it, if I rotate it, I look at this, it's still capybara. It's nothing else. The problem comes in many directions. First of all, we should be cautious, like with some of the cases, like numbers, like 9 rotated, it will not be 9, it will be 6. And much more complicated case is object detection. Like with flipping, we need to track what happened with our bounding boxes. With like coloring, everything is okay. The main challenge is, in fact, rotation, because like when we move geometrically, we can kind of follow what's going on with our bounding box. When we rotate it, it's much more complicated. But in fact, there are already some approaches, some research that applied augmentation to object detection, including rotation, and it was pretty successful. If I'm not mistaken, I put it some link there, so later can explore. Okay, I mentioned like about simple idea to data augmentation. Now, like how, as usual, it works in semi-supervised learning. So I am talking now about images mostly because it's the most straightforward, the most obvious example. But like to text, you can apply similar ideas, just augmentations will be slightly different. So the idea is like this. We have image, we apply 2 different augmentations. As usual, people in research call it like strong augmentation, weak augmentation. After that, go through some network. In most of the cases, it's like classic teacher-student architecture, where we learn student network, but get guidance from teacher, which in fact is exponential moving average of the weights from the teacher. And after that, compare results. As I mentioned before, like if I apply augmentation, results should not be changed significantly. Okay, I'll just give few examples. One of the paper that I like and is pretty straightforward and gave some significant result is stack paper. So the idea again is like this. I'll talk a bit about this paper later, but now just about augmentations. So we just take unlabeled image, we go through network, and at the same time we apply some augmentation. In this case, we just remove some patches. So we have bounding boxes. Bounding boxes here will not be changed, obviously, if we not remove the whole object. And after that, we apply some loss function, compare these images, and get result. Another example with more interesting, in my mind, augmentation, when we have, when we mix up like two different images, apply mosaic, and get results. So you can see there, like on top of the plane, we just add those players, and still can recognize bounding boxes. So result is still clear. I already gave example about augmentations. I explained how we can apply them through comparison in the end, like results should be consistent. And that's what I am trying to show you. So like we have input image, augmented somehow, apply either through neural network or through two different networks, or through student-teacher architecture, get output, and after that, apply some loss function. When we are talking about unlabeled images, we should find some functions that compare these outputs. It can be class, it can be bounding boxes, it can be some embedding, and I just put here a few examples, like some, as I said, like some similarity loss, like KL divergence, like Kullback-Leibler divergence, focal loss, etc. I will show later in other options that are popular now in the research. Okay, that's example from current research. So what people actually do? They take again image, just apply super simple augmentation, flip, send it through neural network. In object detection, like the most popular, again, single stage detector or two-stage detector network, like faster RCNN, or YOLO, the most popular. And they show here that it can be pretty successful. And again, below I give example of loss function. Here they combine localization loss function and location. For localization, they just use kind of L2 different loss functions, kind of quite similar to what guys used in YOLO. And the second one, class, they use Jensen-Shannon divergence, which is which kind of slightly more complicated version of KL divergence, I would say like this. And as I mentioned, it's just simple flip. That's why in localization loss function, we can see slightly strange part of for like x coordinate. A part of these ideas that I mentioned, I just keep here other ideas that make sense to explore if you are interested. So later you can just take a look at presentation and go through this. My favorite example is the last one, mix image tiles and unmixed feature tiles. So shortly, ideas like this. Guys have image, put some patches, mix up them, apply neural network, and on the output do like opposite operation. So I already mentioned a bit about loss functions. Most of them I put here that people use in semi-supervised object detection. Smooth L1 loss, L2 loss I showed in the previous example. I showed Jensen-Shannon divergence, which I said it's kind of derivative of KL divergence, which compare how close are distributions of the data. Yes. Okay. And the next approach, which is, I would say, the most popular in semi-supervised learning, classical version of like classification, I would say from what everything started is pseudo-labeling. So the idea is like this. We have small amount of labeled data. We train a classifier on this data. Obviously, we will overfit. But what we can do, we take this trained overfitted classifier and apply on unlabeled data. After that, look at the results, take the most confident options and add it to our data set. So the idea is like this. If, like assumption, if our classifier is confident, then more likely it's right. Again, this assumption kind of might be correct or wrong, but it makes some sense. And if we iteratively repeat this training procedure, likely we might get better classifier than if we just use labeled data. Okay, and like everything finishes when we don't have unlabeled data anymore. Okay, I already talked a bit about this stack approach, but again, I talk from augmentation point of view now, like how it is related to pseudo-labeling. So algorithm, pretty straightforward. So we first train our model on labeled images, generate pseudo-labels on unlabeled data, and apply stroke augmentation, and after that, like go calculate loss and compare results. And like this loss, as I mentioned in the beginning, and as in all semi-supervised approaches, like contains two parts, like supervised and unsupervised part. Okay, soft teacher. Its idea came from the paper like mean teacher for classification. Idea here is like this. So we have our labeled data, we have our unlabeled data. So labeled data we just process through student. Unlabeled data we process through our soft teacher, through student as well, using different augmentation. And after that, we get some result and compare these results like outputs from two different models. As I said, our assumption results should be the same, so we calculate these losses. Again, unsupervised. Like supervised part comes only from student, unsupervised come from two different directions. Okay, I was talking about pretty straightforward, pretty simple things that return some meaningful result, but it's possibly good for research, for academia, but not good enough for majority of the companies. Recently, I assume people who is familiar with artificial intelligence in depth, like you know the paper clip from OpenAI, where in fact guys trained like pre-trained embeddings for images for text, and like everyone use it. Like I've seen it in many directions, in diffusion models, etc. And actually, the idea, why not to use the same idea in semi-supervised learning? We have some labels, like can we not just blindly use unlabeled data? Can we add some ideas with actually labeling of images, text, etc. So that's the example how we can do it. We just process our images through network, and after that get crops of these pseudo detections, and send these crops through clip, receive some neural predictions of text, and by this augment our data set and improve model training. And finally, what about results? How good is the results? Majority of object detection tasks people measure on two, I would say, data sets, Pascal VOC and COCO. And like main metric is MIP, mean average precision for boxes. Here I just show results for three main directions of models, like one stage detection, two stages, and they call it like end-to-end transformer-based strategies. And actually, results in my mind are quite exciting. So people used here, like below, you can see like 1% of data, 5%, and 10. And for 10% of the data, of the whole data set, I mean 10% labeled data and other unlabeled. The top is like 45, like 50 MAP. For the comparison, for the whole labeled data, if I recall it right, current state of the art is 65. So kind of close, comparing the fact that it's just 10% of the data. From budget investment point of view, it's, in my mind, quite significant. Okay, and like conclusion, what is semi-supervised learning? I asked ChatGPT that many of us like, and ChatGPT answered pretty correct. So it's machine learning approach that combines small amount of labeled data with large amount of unlabeled data. And the main idea is loss typically combined from two parts. Yeah, that's kind of makes sense. Thank you so much. I'm happy to answer on questions that you have.